Alright, good morning class. Today what we're going to do is we're going to talk about this force called gravity. And I know it's one that most of you seem to be most comfortable with because it is the one that you experience every day. And it's the one that's pretty obvious. It's the force that you guys feel that is pulling you towards our planet Earth. And it's the one that I think you guys are just most comfortable with because it's the one that you can sort of not really see it, you can't really feel it, but you can really definitely experience it. But in a nutshell, when we talk about the force of gravity, it is actually a very weak force, one of the weakest forces in the universe. It is, however, the force that does allow our planet to orbit around the sun. It is the force that allows the moon to orbit around the Earth, and it is, in fact, the force that allows our sun to orbit around the Milky Way galaxy, or the center of the Milky Way galaxy. So it's a very important force, and it's one that we're going to take a look at today. Now, it turns out that if you look around the classroom, every one of you guys in the class has mass. So the very fact that you guys possess mass tells us that, well, because you have mass and your neighbor has mass, well, it turns out that any two things that have mass are attracted to each other. Now, of course, we're not talking about a romantic attraction. We're talking about just an attraction between anything that has mass. That pencil that you're holding in your hand, that has mass. The cell phone that you have in your hand, that has mass. And of course, you guys have mass, so therefore you are all attracted to those things just as much as they're attracted to you. So if you think back to Newton's third law of motion, it stated that for every action, there's an equal and opposite reaction force. So, and I think I gave you an example the other day that involved Phil Kessel of the Toronto Maple Leafs and Mike Camilleri of the Montreal Canadiens. So we said that if one hockey player pushes another hockey player with a force of, let's say 200 newtons, turns out that the other hockey player will apply the exact same force back on the person that did the pushing. So I'm going to use a slightly different example this time. Let's suppose we had Earth over here. So I'm going to draw Earth. Yeah, that's a pretty good Earth. So we've got planet Earth over here. And I also know for a fact that we have the moon, which is slightly smaller in size there. So there's the moon, some distance away from the Earth. And as you guys all know, the moon does in fact orbit around the Earth. Okay, along a circular path. And if I take a look at the Earth-Moon system in this particular example, I want you guys to have a look really quickly. I know for a fact that the moon is going to be attracted towards the Earth. Okay, and it's attracted towards the Earth because of this force due to gravity. All right. So here's the action force, if you will. I mean, it doesn't really matter what you label to be the action or the reaction force, but let's just say that the action force is the moon being pulled towards the Earth with this force due to gravity. Well, then the reaction force would be that Earth is being pulled towards the moon with another force due to gravity. Okay, and that force of gravity is, of course, due to the masses of these planets. Now, if you compare these two forces of gravity between the Earth and the Moon, turns out that these two forces are actually identical to each other. Okay, those are the actual action and reaction forces. All right, and if you take a look, the only reason why they're actually attracted to each other is because both the Earth and the Moon have mass. Now, I know you guys might say, well, this seems kind of odd because I know for a fact that Moon is definitely pulled towards the Earth, but yeah, actually the Earth is going to be pulled towards the Moon as well. But then, of course, you might say to yourself, well, why don't we actually see the Earth being drawn towards the Moon or accelerating towards the Moon? Well, the answer is it actually is. Okay, but the reason why you don't physically see it is because, well, if you were to compare the masses of the Earth and the Moon, well, there's quite a bit of a difference there. So Earth being the more massive planet or the more massive object, obviously has a lot more inertia as well. But we're going to talk about that a little bit later on. So what we're going to say is that, if you take a look around the classroom, all of you have mass, so you are all attracted to, well, your fellow neighbors over there. So here's the thing. This force of gravitational attraction, I'm going to label that as F with a subscript capital G. That happens to be related to the product of those two masses. So if you know what the mass of one object is, and you know what the mass of the other object is, if you take the product of those two masses, it turns out that this force of gravitational attraction is directly proportional to that that product. Okay. There's a second thing, though. There's a second thing that this force of gravitational attraction is dependent upon. So if I were to take a look at Earth all over again, there's Earth, very nice. You guys are all standing on the surface of the Earth. Keep in mind, class, this is not a scale diagram, and I'm not a very good artist either. So here's the thing. So I know for a fact that if you look at this diagram over here, our planet Earth has mass. The person standing on the planet also has mass. Okay, so we can say that the person is attracted towards the Earth with the force due to gravity. I also know for a fact that the Earth is attracted to this person with the force of gravity as well. So the question then becomes, well, how does this force of gravitational attraction depend upon the distance between those two objects? Well, right now, you can see that the two objects are actually in contact with each other. They are only separated, or the centers of the two masses are only separated by a distance between the center of the Earth and the center of that person, which is approximately the radius of the Earth. So what happens now if the person decides to how do you do this? What if the person decides to move a certain distance away? So if the person decides to move further outwards over here, okay, and then even further outwards over here. So what happens as the person gets further and further and further away from the center of the Earth? Would the force of gravitational attraction get stronger, or would the force of gravitational attraction get weaker? Turns out that the further away you get, or the further apart the two masses happen to be, the weaker the gravitational field. And what we're going to say is that if we were to draw a relationship to show what that relationship looks like, well, let's take a look at this graph over here. Those two lines, by the way, are supposed to be joined. I don't know why it's not like that right now. But if you take a look at the y-axis, we have force of gravitational attraction. On the x-axis, we have r, which doesn't stand for radius, actually. It's nothing more than the distance between the two masses. And that's what r stands for. Okay? We just use the r in this case because, well, as you can see, a lot of times when we talk about things orbiting other, planets or suns or whatever it is, that orbit is a circular one, and, well, the distance between it and the center of that planet or sun that they're orbiting happens to be the radius of the path. So that's why we often use r. But here's the thing. If you take a look at the graph of force of gravitational attraction and the distance between the two objects, it turns out that we get a graph that looks something like this. Okay, so as the distance between the two objects gets really small, the force of gravitational attraction gets really large. On the other hand, as the two objects get further and further apart, the force of attraction obviously weakens. Okay, now you can see in this case that we actually have a horizontal asymptote at the x-axis, and what that basically means is that if you take a look at this graph over here, as r were to increase to an infinite distance, this force of attraction never quite gets to the x-axis. It gets as close as it can, but it never really quite gets to exactly zero. It'll be 0.000000 something, but it never quite gets there. So that's why we often show the asymptote, and you can see that there's also another asymptote along the y-axis as well. So what we're going to say in this case is that this force of gravitational attraction, not only is it dependent upon the product of the two masses, but it's also inversely proportional to the distance separating those two objects squared. Okay? So we have two things that this force of attraction is now dependent upon. You talked about this force of gravity being dependent upon the product of two masses, and also being dependent upon the inverse of the distance separating the two objects squared. Now when you put these two relationships together, we can turn that into an equation by including a variable on the right side. And when you include the variable on the right side of the equation, what you actually end up with is, you end up with the following equation. And this is the equation that you might, or if you take a look at your formula sheet, it's the one that's already provided for you. Okay, so the force of gravitational attraction is equal to G. Now you might say, well, what's this G? What's this capital G? No, it doesn't represent gravity. What G represents in this case is something that we refer to as the universal gravitation constant. Okay, and it actually has a value. Now again, we're not going to go over how this was derived because frankly I don't know right now, but it is something that you are not required to know, but it is something that you're going to be using every single time you use this equation, and that constant turns out to be equal to 6.67 times 10 to the power of negative 23. Let me just shift this over a little bit. And the unit associated with the universal gravitation constant is Newton meters squared per kilogram squared. Again, it's another constant that's provided for you guys on your formula sheet. All right, so hopefully that makes some sense right now. What I'm going to do is, let's see if I can zoom out here. Okay, let's just see if I can get this all on one page. By the way, class, I don't know if I left you this handout or not. If I didn't give you this handout, don't worry about it. I will provide it for you guys on Monday, but you will need it for tonight's homework regardless. Yeah, if I go back to this previous page, oh wow, I did make that mistake. Okay, class, if you can do me a favor, on the previous page I did make a mistake. I wrote down 6.67 times 10 to the power of negative 23. I really don't know what possessed me to do that. So if you can do me a favor, I need you guys to make a change for me. It turns out that's not 6.67 times 10 to the power of negative 23. That it is instead, hang on a second, I don't know why it's not allowing me to delete. It's supposed to be 6.67 times 10 to the power of negative 11 Newton meters squared per kilogram squared. So if you can just go ahead and make that change, and we'll flip to the next page. All right, so if I turn over to the next page, we have the following. So that equation that you guys just saw, looks rather intimidating, and I dare you guys to put that in the form of one of those magical triangles that you guys like to create. Trust me, it doesn't work. So this one over here is a little bit different. You know that a couple of weeks ago, I did mention that the force of gravity that you feel, or what you feel towards the center of the earth, or the attraction that you feel towards the center of the earth, is often given a special name. That force of gravity is often referred to as your weight. Okay, now it turns out that this weight that you possess is dependent upon, well, first of all, the fact that you have mass, and that your mass is being pulled towards the center of the earth. Well, because you are standing roughly on the surface of the earth, what we're going to say is that you are all subject to Earth's gravitational field. Okay, and it turns out that I shouldn't say at exactly, but at the surface of the Earth, that gravitational field that Earth exerts on every single mass is approximately 9.8 newtons per kilogram. Okay, so well, we can put those two things together, and we can say that an object's weight can now be determined by using the following equation. It's actually a much simpler equation, and it looks something like this. F with a subscript little g now is equal to the object in question. Let's say if it's you, it's your mass. If it's a soccer ball, it's the soccer ball's mass. So that mass times g, the gravitational field. And in this case, if you take a look, this equation looks a lot easier to use than the one that you guys just came up with in the previous slide. Now, in this case, again, this formula is given to you as well, but this value little g, okay, it is also a constant. Okay, now it's not the universal gravitational constant, but this one is actually the constant to represent the gravitational field. Okay, and near the surface of the Earth, this value of g is going to be equal to 9.8 newtons per kilogram. And I think most of you can recognize that, wow, that looks like the acceleration due to gravity. Well, it is. It just has different units associated with it. If we're dealing with an object actually accelerating towards the center of the Earth, if you want to use that in your other calculations for kinematics, yeah, you would use 9.8 meters per second squared. But if we're talking about an object's weight, or the force of gravity that it is subject to, we're going to say it's 9.8 newtons per kilogram. So how do you use these equations? Well, let's see if I can take a look at this example down here. What we have is a 60 kilogram person who is standing on the surface of planet Earth. So I've given you guys a couple of variables as well. These things you don't have to memorize. They will always be provided for you. I've also given you the mass of our planet Earth. I've also given you the radius of our planet. Okay, now I shouldn't say the exact radius, but the approximate or average radius around our planet as well. So let's take a look at how you would determine your weight near the surface of our planet Earth. So if you take a look on the left column here, we have weight, and I'm going to write down the equation. And write down the equation for weight. F little g is equal to m times g. So we said here in this case that m represents the mass of the object that is subject to the gravitational field. And in this case, that object happens to be a 60 kilogram person. Okay, so 60 kilograms is the mass. G is, of course, the gravitational field that this mass is subject to. So if we're talking about the Earth, we know that the gravitational field near its surface is 9.8 newtons per kilogram. So if you do this quick calculation, it actually turns out to be 588 newtons. Okay, so in other words, what we're going to say in this case is that that person's weight is going to be 588 newtons. We also know for a fact that force is a vector quantity, so you might say, well, what direction is that going to be in? Generally speaking, it's just towards Earth's center. Okay, I can't really say up, down, east, west, whatever. I can't say those things because it really depends on where this person is standing with respect to, the center of the Earth. So if you take a look, 588 newtons would be your answer. That was actually a really nice equation to use. Very simple, one that you're going to be using a lot in tonight's homework. Now, what about this equation for universal gravitation? Well, how would you use this in your calculations instead? Well, let's take a look at this equation, at the equation for universal gravitation. It's F subscript big G being equal to G m1 m2 divided by r squared. Well, let's just plug in some of the variables that we know so far. Now, if it's okay with you guys, I'm going to zoom in because it looks like I'm going to be running out of paper here. So we know our value for G, which is our universal gravitation constant. That happens to be 6.67 times 10 to the power of negative, did I say negative 23? Oh, you know what? I think I did. You know what, class? I made a little boo-boo. If you can do me a favor and let's see if I can go back to the other page again. So, alright, so here we go. 6.67 times 10 to the power of negative 11. Now, if it's alright with you guys, I'm going to leave the units out for now, just because, well, actually, no, let's not leave the units out. Let's just include them because, you know what, I think I just might have enough space. So 6.67 times 10 to the power of negative 11 Newton meter squared per kilogram squared. Okay, so there's my universal gravitational constant. It's all this multiplied by m1 times m2. So I know for a fact that m1, let's just call that the mass of the Earth, is 5.98 times 10 to the power of 24 kilograms. And m2 is the mass of the person, which is, of course, we know 60 kilograms. And you know what, of course, since we're including the units, I forgot to put that in here as well. 5.98 times 10 to the power of 24 kilograms. And the mass of the person is 60 kilograms. Now, I don't know if you can see this or not, but most of you can see that this kilogram times this kilogram would give you kilograms squared, and it would cancel out that one over there. And it's all of this divided by r squared. Now what's r? It's the, in this case, the radius of the planet, so 6.38 times 10 to the power of 6 meters. And again, that's going to be squared. And I don't know if you can see this or not, but if you take a look at the denominator side, meters squared, well, that becomes meters squared. And if you take a look at the numerator side, we have meter squared over there, meter squared over there. They cancel out, and therefore your units cancel out. Now keep in mind, don't forget that that squared, you still have to square the 6.38 times 10 to the power of 6. So let's just do a quick little calculation over here and see what this force of gravitational attraction turns out to be. And punch a couple of numbers in your calculator, and oh, look at that. Turns out to be equal to about 588 newtons again. Okay, now that happens to be the mutual force of gravitational attraction between the person towards the Earth, which might be your action force, and it's the same force of attraction that draws Earth towards the person, which would be, of course, your reaction force. So if you take a look, this equation just gives you the magnitude of that force of attraction. The direction would be, of course, dependent upon what you're stating the direction with reference to. So if I zoom out of both of these, oh, look at that. We got the exact same answer here, 588 newtons over there. So the question might be, well, wow, if this equation over here is a lot easier to use, then why are we using that equation instead? Well, the equation for weight is going to be used in cases where you know what the value of the gravitational field is going to be at a certain location. So in this case, we know for a fact that if you're standing on the surface of the Earth, I know that the gravitational field is 9.8 newtons per kilogram. So this is a very convenient equation to use. On the other hand, if I don't know what that gravitational field is around a particular mass, I would be subject to using this equation. Now, it is also called the equation for universal gravitation, and the reason why it's called that is because you can use this equation for any two objects or any two masses separated by any distance anywhere in the universe. So we can use, so this is very convenient to use for objects such as planets and stars, things out in space, or even for things that are as simple as, you know, the force of attraction between you and the neighbor beside you. Okay, so it can be used for anything, any two masses that are separated by a distance. Okay, and I think I'm going to leave it at that for now. And over the weekend, I think I might be posting one last video for homework tonight, class. I know you're not going to like this, but if you can begin bullet number 5 in your textbook, that would be much appreciated. Thank you.